Thank you very much. Let's see if this works. Okay, great. So I would like to start by thanking the organizers for putting together this great event, and to all of you for coming, even this late. And okay, so I would like to also thank the organizers for giving me the opportunity to present our recent work. This is done in collaboration with Julian Kupka and Charles Strickland Constable, and it concerns these works. And so what I want to talk about is some new developments in the relatively old subject of n equal 1, d equal 10 supergravity. So there will be two topics that I want to talk about. One of them is a simplification that one can do in order to study the n equal 1, d equal 10 theory, including fermions to all orders. And the second one is how to build a BV formulation of this theory. So as far as we are aware, this is the first time that a BV formulation of a higher dimensional supergravity has been written down in a sort of background independent way. And so this is made possible by some very, very useful tools. So there will be two of them. First one is the so-called generalized geometry, which you can think of as simply as some sort of efficient repackaging of fields and action and symmetries in some sort of smaller amount of variables, in a way that where you don't introduce any extra fields, any auxiliary fields, and you don't remove anything. So it's really the same stuff, except it's like a more sort of concise language. And in particular, one of the advantages is that the Young-Mills supermultiplets are included for free, including their coupling to the theory. And of course, it's fully geometric as well. And the second simplification, which seems to have gone sort of underappreciated in the literature, is this fact that you can, in fact, just do things directly. And the message I'm trying to convey is that you can just work with metric formulation directly. You don't need to introduce any field binds or Lorentz symmetry in order to tackle the coupling of fermions to gravity and all that. So you can just do things directly. There will be some interesting geometry behind this, of course, but as you will see. But yeah, and in particular, this considerably simplifies the structure, because now you don't have, when you don't have Lorentz symmetry, then you only have the diffeomorphisms, the B-field gauge transformations, the gauge transformations for the fields, and the local supersymmetry. And you will see that the algebra is very, very small, kind of. And this fortunately applies to supergravities in all directions, while this generalized geometry framework is specific to 10D, at least in the way I'm going to present. Okay, so that's the outline. Now, so what is this theory in question? You perhaps all have seen it. So, the only data that you need to specify in order to build this theory, because of the large amount of supersymmetry, is a Lie group or Lie algebra, at least locally. Globally, you can do some interesting patchings. But for local description, you only need to have a Lie algebra with an invariant pairing, and then you can construct the following theory, where the bosonic field content is the graviton, the B field, gauge field, a dilaton function, and the spinners, or the fermions, which are spinners. In particular, gravitino is a vector spinner, so it carries a vector index. Dilatino is simply a spinner, and gaugino is a spinner valued in the Lie algebra. And so the action for the theory looks like this. Perhaps you are most familiar with the beginning, which is the bosonic bit. And occasionally you might glimpse these quadratic fermionic terms. So this is this kind of red or purple, red color. And the thing you don't see at all, unless, okay, almost don't see at all, is this quartic fermionic terms. So as you see, like, it goes quite beyond the bosonic bit. And the claim is that this is invariant under the following set of supersymmetry transformations, where again, the red ones are highlighted, like these are the higher fermionic ones. And so this theory was constructed in these papers, essentially, in the 80s. But I want to point out the thing that if you look into those papers, then the formulation you will find is substantially longer. And the way I presented it here is kind of a result that we got from our work in generalized geometry, in that, for instance, we showed that it's possible to organize the theory in a way where, for instance, you only ever encounter gamma 3s, so gamma with 3 antisymmetrized indices in these higher terms, and you never have any contraction of gravitini with the gamma matrix indices. And it will be clear in a moment why that is the case. So yeah, so already the way the result that you can write this theory in terms of classical variables, so these things like this, that's kind of a consequence of the generalized geometric treatment, and it's not at all obvious when you just start by reducing 11D theory. But the formulas I'm going to show you in a moment are much simpler, actually. In generalized geometry, these things significantly simplify. So what is this generalized geometry? So some sort of crash course. In fact, the only thing you will need to know is that the starting point is simply, you look at your theory, so supergravity, you look at its local symmetries, so you have diffeomorphisms, you have one-form gauge transformations for the B field, and you have some gauge transformations for the connection, for the gauge field. So you just put them together in this kind of formal sum in this new vector bundle over, let's say, R10, and you notice several features. For instance, there is an interesting bracket, inner product on this space where you can just pair T with T star, and you pair Lie algebra with itself using the invariant pairing. There is also a natural map that projects the stuff down just to the first component. And most importantly, there is a bracket which takes this form and which is capturing the symmetry algebra here. So that's one way to arrive at such an object. Notably, this bracket here satisfies the Jacobi identity, although that's kind of not obvious. Okay, so having defined this, now we can start encoding the fields. So the claim is that the bosonic fields are easily encodable by taking simply these two objects. So we define a generalized metric to be a map from this bundle to itself, which squares to the identity. This is just a fancy way of saying that we are splitting the bundle into the plus minus one eigenbundles of G. So this is the same data as splitting of the bundle into 2 bits, which are orthogonal. So we will call them C plus and C minus. And so the way you encode most of the bosonic field content is simply that you draw this picture. So you have tangent bundle, you write the rest. So this is together, this plane represents E. And then if the dimensions were, if you restrict your attention to some specific subbundles of some specific rank, then you will see that the C plus looks something like this, and you can read off that this is a graph of some linear map from T to the rest. And if you look at it, then that's precisely metric plus B field plus A field. Right? So because the map from T to T star has a symmetric and antisymmetric part, that's G and B. Map to G is simply the connection. And so the only bosonic field that is missing is the dilaton. So the dilaton is simply encoded here as a half density. So H here is a line bundle of half densities on the manifold. That's going to be very important, sort of. Also, but this is not a new treatment. Like it's kind of this is the factor that appears in the string effective action anyway. So this is how you read off your usual functional treatment of the dilaton. Okay, so this is the bosonic fields. Now the fermions are actually not much harder. So if you assume that the signature is 9, the induced signature on this subbundle is 9,1, which is what you want for supergravity, and we define the Majorana-Weyl spinor bundles for this subbundle C+, we call them S plus minus. Note that we will not use spinors for C minus, only spinors for C plus, because this is type 1 theory. So having defined these subbundles, now you just proceed and you just declare that this is your fermionic content. So there is a generalization of the dilatino, where this capital pi simply stands for parity shift. So this just means that the field is bosonic, fermionic. And you see that the dilatino is a spinor of some chirality, but it also has a half density component. So it's not a function, it's a half density. That's kind of important because it turns out that this kind of eats a lot of nasty terms in the variations and in the action. So this is kind of like a field redefinition. You multiply it by the dilaton. But in any case, the more important one is the gravitino, which turns out to have, as you saw before, it has a spinor index of opposite chirality. It is a half density, but it's also a vector. But now the most crucial observation here, observed in these papers, was that the vector part of the gravitino is living in the C minus bundle, while the spinors here were constructed for C plus. Which means that, for instance, if you are going to write some bilinears of these things, then you are never allowed to contract the gamma matrix indices with the vector index on psi in generalized geometry. That's like just not possible. So this thing tells you that there is only a couple of things that you can write that respect the symmetry, and it turns out that those are precisely the terms that appear in supergravity. Okay, and just one last technical term. Without going into details, so in generalized geometry, there is a way to construct natural analogs of operators in Riemannian geometry. So you can construct scalar curvature, Dirac operators, etc., etc. And here I'm just adopting the convention that Latin and Greek indices stand for some frames in C plus and C minus, respectively. Okay, now with all that, I can just tell you that this is the result. This is the action written in those variables. So the orange part goes back at least to the work of Siegel. Anyway, let's say Siegel in '93. So that this is the entire bosonic part of type 1 supergravity. The fermionic part, in the lowest order, was known already in these papers and constructed also, the variations were also constructed. And so now what we did essentially is that we observed that there is only very small number of terms that you can write when you respect this kind of structure of the index structure. And it turns out that these are the only two terms that you can write up to some coefficients. So we wrote those two terms, put some arbitrary coefficients. We put some arbitrary higher spinor variations here, put some arbitrary coefficients in front of those, and then we just checked by hand that for these numerical values, the action is actually invariant to all orders. And you can do that check by hand. It took quite a while, but it's actually written up in the paper. It's just a couple of pages calculation, which is also, maybe I'm wrong, but I think that's probably the first time that such a calculation was exhibited in a paper, like explicitly. So this kind of like a direct proof of supersymmetry without relying on any other arguments. But okay, you can go further. So you can study the symmetry algebra. So as we said before, this bundle E was already constructed in a way that it encoded all the bosonic local symmetries. So sections of these zetas, they are formal sums of diffeo or infinitesimal diffeos, one forms and gauge transformations. And in generalized geometry, there is again a natural counterpart called generalized Lie derivative, which kind of encodes this action on all the fields that we saw before. There is, as was mentioned also before, the one-form gauge transformations are reducible. So strictly speaking, you have to include some ghost for ghost, but that's not terribly important. What's more important is the symmetry algebra. So this is actually a deceptively simple-looking result, behind which there is quite a long calculation done by Julian. So the result. So this is the symmetry algebra of supergravity. Once you exclude all the, if you do it directly in the metric formulation without any field binds or Lorentz transformations. So you have there, as expected, the two diffeos close into a diffeo and SUSY give you a SUSY. And the commutator of SUSYs, which is the most important and most interesting part, is given as you would expect, or as is expected in supergravity theory. There is, most importantly, there is a diffeomorphism term, which is constructed out of epsilon1, epsilon2 in this way. There is also supersymmetry, which is of higher order in fields, and which depends on the dilatino. So this is not unexpected. But what is kind of slightly unexpected is that this is all, and there is like really no need to include any. There is no Lorentz transformations actually appearing here, and in fact, even the part proportional to equations of motion can be written down. Which again, I'm not aware of a paper where this would be written down. I mean, maybe there was one, but definitely not in the old papers. But anyway, the claim is that you can show that this is what's happening. This is the algebra, and okay, and then you can go further, and you can ask a question that you, in principle, could have asked also on the previous slide. So you can ask, what is actually the meaning of these objects? Like, what is the geometrical meaning of these variations? Because spinors. The fermions are spinors, and spinors are defined with respect to an underlying metric. So they are sections of a spinor bundle constructed for a given metric. And when you are making a supersymmetric deformation of things, then you are also changing the metric, which means that this thing, which should stand for some infinitesimal difference of two objects, it cannot really be an infinitesimal difference because it's like the new spinor lives in a different space than the old spinor. So what is actually the meaning of this? And the meaning is kind of nice and geometric. The meaning, oops, oh, I see. This is what happened. Okay, so the meaning is that the field space really has the following bundle structure, that you should really look at it as having at the bottom the space of bosonic configurations, and the field space itself being the total space of this bundle, where the fibers are given by the fermionic configurations. And the kind of non-trivial claim, but not difficult to show, is that this bundle actually possesses a natural connection, which is, however, not flat. And this is the thing that allows you to identify nearby spinors for nearby generalized metrics. And so the picture to have in mind is this one. So this is the square is the whole total space. So this is the space of all fields. This diagonal red arrow, the delta, this is simply asymmetry, like let's say supersymmetry or generalized diffeomorphism. And right, so symmetries are vector fields on the field space, right? So this is the red arrow. But now using the connection, you can split this into a vertical and horizontal part using the connection, and that's precisely what the meaning of these symbols is in this kind of geometric metric approach. And as I said before, this connection has a curvature. So connection here, you see that it's represented by these blue lines. These are the horizontal spaces. And this connection is curves. It has a curvature. And this is kind of the technical reason why the Lorentz terms don't appear. I didn't present the calculation, but if you do the explicit calculation, then you will see that the way these Lorentz terms disappear is if you correctly take into account the curvature contribution when calculating this commutator. So, okay, I'm happy to discuss that later on. And maybe just to finish, let me show you the full BV supergravity, the BV formulation. So as we said, the physical fields are, well, these four guys. There is supersymmetry and generalized diffeomorphisms. That's all there is to symmetries. So we call them the ghosts, we call them E and Xi. And there is a ghost for ghost. And then there is antifields to each of them. So as usual in BV formalism. So I will denote them by star. And then this is the action. It might not look short, but it is very short. And if you know about BV theory, then the way you should read this is that the first two lines tell you what the classical theory was, what the theory you started with was. The next three lines simply encode the symmetry transformations. They tell you, like for instance, if you're interested in how rho transform under supersymmetry, you should look up the rho star line, and you should look at the terms which contain the Susi ghost. So this is the supersymmetry transformations. So this is how you read it. Next line is simply the symmetry algebra. So this encodes these hard calculations about the commutators of supersymmetries and all that. The next line is, okay, this is less intuitive. This is the ghost for ghost contribution. But the important bit is the last line, which is quadratic in the antifields. And this is the thing that is responsible for non-closure of the algebra. And now the really non-trivial claim about this action that I wrote is that it satisfies the classical master equation. And that we, again, provide a full proof in the paper. It's now a bit longer than the preceding one, but you can do it. And hence, you now have a BV formulation of supergravity. And you can proceed and do things that you would like you can try to attempt some sort of quantization, or you can study anomalies, or you can study some other things. So now what can one do with this? So first, some conclusion. I guess there is, okay, perfect, thanks. So, okay, so as said before, so or as you saw before, this essentially completes the program of like reworking n=1 supergravity in generalized geometry. It is simple enough so that you can do a check about supersymmetry by hand, in principle. And as far as I know, it's the first BV formulation in a background independent way of a higher dimensional supergravity. So up to now, I think there is like 4D and 3D, and now there is 10D. And it also confirms once again that generalized geometry kind of provides the right or the natural set of variables to use for the string massless sector. And in order to do this, just as a technical simplification, we use this direct metric approach where we avoided the Vielbein and the Lorentz transformations. And okay, just further interesting games that you can play with it are these two games, for instance. So once you formulate stuff in generalized geometry, then it turns out that there is some sort of special corners which you didn't see before. And one of them is, for instance, you can set this endomorphism G, you can set it to 1, in which case all the metric degrees of freedom and the associated spinors decouple. And the only thing that you're left with is this theory which has these kind of generalization of dilaton and dilatino. And it's topological and it's locally supersymmetric. And it's kind of like an interesting toy model. So we first figured out the BV formulation in that model, actually. Or you can take a second interesting limit. You can take your base manifold to be a point, and this turns out surprisingly to fit into the thing. And if you do it in a clever way, then you still keep the entire structure of supergravity, all the supersymmetry variations, the BV formula, like all the action, the long one from the preceding formula, but it's not finite dimensional. As is like the field space is finite dimensional. And so now the outlook, what you can do, one can try to do type 2, which is another place where where generalized geometry is useful, or you can study some cool things such as the conjecture of Costello and Lee about the topological, or sorry, the topological should not be there, about twisting of supergravity and the way it links to the Kodaira-Spencer theory. So these are kind of interesting things for the future. So thank you. Okay.
Is it on? Oh. So you said that with this construction, it does satisfy the classical BV master equation.
Mm-hmm.
Any indication what you would expect if you would ask for it to satisfy the quantum BV master equation, and what you will have to like deform in the algebraic structure of the theory?
Mm-hmm. Okay, thank you. That's a very good question, a very natural one. So all sorts of, well, in quantizing the quantizing this theory would be kind of complicated, but what you can do, and what was done by Costello and Lee, is that you can perform a twisting of the theory. You can kind of move away slightly in this BV space from the locus that you normally study, and then the theory that you have becomes sort of much more simpler while still retaining many of the features of the original theory. And that one you can show, or they show that you can perturbatively quantize in like a rigorous way even. And so yeah, I mean, in building up the solution to quantum master equation, there is like all sorts of complications because this is like a, well, it's a very physical. I mean, it's a very big theory, so it has, you need to do it in a complicated perturbative way, and I don't know much about that, but you can look at the works of Costello and Lee where they do that in this twisted regime.